In the sphere of space exploration and infrastructure, one of the most audacious and groundbreaking concepts that has transitioned from the realms of science fiction into the purview of serious scientific discourse is the construction of high-capacity orbital elevators for space access. Imagine a world where reaching space is as routine as catching a flight to another city. The construction of a massive elevator stretching from the Earth's surface into geostationary orbit promises to revolutionize the way we access space, making it more economical, reliable, and available to a multitude of industries. This is not a mere pipe dream. With advances in material science, particularly the development of carbon nanotubes and other super-strong lightweight materials, the potential for building structures extending well beyond our atmosphere is coming into the realm of possibility. The proposal of such an elevator is not only a testament to human ingenuity, but also a solution to the current cost, prohibitive and environmentally damaging rocket launches, which are our only means of carrying humans and cargo to space. Diving deeper into this enthralling subject, let's embark on a comprehensive journey through the physics, challenges, and potential of constructing high-capacity orbital elevators. This game-changing infrastructure could quite possibly be the key to unlocking a new era of space exploration, industrialization, and colonization. To understand how an orbital elevator would operate, it's imperative to grasp the concept of geostationary orbits. Located approximately 35,786 kilometers above the Earth's equator, satellites in this orbit rotate with the same speed as the Earth's rotation, allowing them to remain stationary relative to the surface. An orbital elevator, or space elevator, leverages this concept by anchoring a cable or tether on the Earth's surface, extending it to a counterweight well beyond geostationary orbit, creating a balanced system where centrifugal force due to the Earth's rotation keeps the structure taut and stationary relative to the Earth's surface. Now, let's unfold the layers of this concept and discuss the architectural design of an orbital elevator. At the heart of this is the cable, a long, thin ribbon made of an exceptionally strong and light material, as no conventional substance can withstand the immense stresses exerted on such a structure. The most promising candidate for this is carbon nanotubes, which are theoretically able to have the tensile strength necessary to support the cable's weight and the additional load from climbers. These climbers, which can be visualized as motorized platforms, would ascend and descend the cable, carrying cargo and passengers to and from space. As one might imagine, powering these climbers would be an engineering feat in itself. Solar power, magnetic levitation, and even laser power beaming have been proposed as potential energy sources for the climbers. Discussing the benefits of an orbital elevator brings a bounty of transformative advantages. Primarily, it could drastically reduce the cost of putting material into space. Compared to rocket launches, which are held back by the need for massive amounts of propellant and can cost thousands of dollars per kilogram of payload, an elevator promises a gentler, more steady climb to orbit. With a permanent structure in place, the only limits to capacity would be the number and speed of the climbers, making it feasible to send up larger structures, supplies for long-term space missions, and even large groups of people. This efficiency could pave the way for space tourism, lunar and interplanetary missions, and even off-Earth mining ventures to become a practical reality. The construction and operation of an orbital elevator also embody a series of formidable challenges. Space debris poses a significant hazard, as even a small object traveling at orbital velocities can sever the elevator's cable. Mitigation strategies could include shielding, real-time debris tracking, and evasive maneuvers. Another challenge lies in the sheer scale of the project. Building an orbital elevator would require an international effort, massive funding, and a legal framework to address the use of geostationary orbits and the implications of having a fixed structure piercing different layers of airspace. Furthermore, the potential impact on the environment and the political implications of such a structure cannot be overlooked. Climbers ferrying payloads to space would no longer need the explosive propellant-driven escape most rockets use today. This means that payloads could be more delicate and potentially include human travelers without subjecting them to the intense stresses of a traditional launch. This less violent ascent could expand the possibilities for what we can send to space, from intricate scientific instruments to fragile ecological biospheres. Additionally, with decreased launch costs and increased accessibility, universities and private companies could open new frontiers in space science and technology development, making the dream of a truly spacefaring civilization within our grasp. Zooming out to entertain the broad implications of having a reliable space access point, we ponder on a future where space elevators could transform economic models, resource management, and even the geopolitical landscape. The elevator could be a critical infrastructure for a circular space economy where raw materials from asteroids or the moon could be brought down for use on Earth while we send up modules to build space habitats or fuel depots, all at a fraction of the current cost and environmental impact. As we conclude this exploration of high-capacity orbital elevators, it's evident that the realization of this technology represents one of the most significant leaps in human advancement. Bridging our world with the cosmos through this celestial tether, if accomplished, will be a monumental engineering and collaborative triumph, marking the dawn of a new epoch in space exploration and exploitation. The vision of elevators to the stars is more than just a testament to human imagination. It is a beacon of our unyielding pursuit of progress, with the stars not as distant dreams, but as destinations within our reach. Building high-capacity orbital elevators for space access is a fitting testament to humanity's insatiable curiosity and boundless ambition to reach beyond the skies and into the stars, forging a pathway not just across the heavens, but toward our collective future as a spacefaring species. As we gaze up at the night sky, it's thrilling to ponder that one day, a line, a ramp to the cosmos, could literally connect us to the vast expanse, transforming the human story in ways we're only just beginning to imagine.